For example 3, what I want us to do is draw a triangle. Just a little basic, okay, like this. Okay. And what we're going to have is, you know, I've been trying to find x all this time, right? So I'm going to put x, I'm going to make x an angle, because that's what this is about, finding angles. Okay. So if I've got this angle over here, suppose, just as an example, and they'll give you a whole bunch of different variations on this, right? Suppose I know this side over here, and I know this side over here. Okay? Now, we've looked at these kinds of things before, right? What we need to do, we always need to start by identifying which sides have I got in relation to this angle, right? I can choose from adjacent, hypotenuse, and opposite, right? So which ones have I got?
2 centimeters hypotenuse.
This one's the hypotenuse, good. And this one's the opposite, which is why it's sine, okay? So I'm going to write an equation here. It's going to be sine of this angle, right? X degrees, is equal to opposite on hypotenuse. SOC right? So opposite on hypotenuse, right? So that's just going to be a half, yeah? A half. Okay. Now at this point, I am in exactly the same position that I was here and I was here, right? I've got the x here, but there's just this one thing I need to get rid of. There was a +2 I had to get rid of, so I did -2. There was a ×3 I had to get rid of, so I divided by 3.
That's division.
I have a sine here. Now sine is an operation or a function just like plus and multiplication, but it's a bit unoriginal. The inverse, right, like subtraction or division, the inverse of sine is called sine inverse. Okay, and you can see it there. I alluded to this a few days ago. On your calculator, it's above shift. The sine button, yeah, you hit shift and then sine. It'll get that. Right? Shift and then sine. Okay. So, if I do sine inverse to both sides, I've got sine inverse of sine x. So I did sine inverse on one side. I'll do sine inverse on the other side, like that.
How do you write that in the calculator?
Okay, yeah, I'll show you in a second. Okay, so what have I got here? All I did was, just like both sides here, I took away 2. Both sides here, I divided by 3. Both sides here, I've done sine inverse. Okay. Now, here's what's going to happen. Just like here, +2 -2, you just get x, right? ×3 divided by 3, you just get x. Right? So what's going to happen on the left-hand side?
You just get x.
You just get x. The sine inverse and the sine will cancel each other out. Okay, so you just get x 3's over here. Okay, and now I just need to punch this into my calculator. Just like I had to do 3 -2 and to 24 divided by 3, you're going to go to your calculator and say shift sine. Right? Shift sine. Okay, good. This will come up. Sine inverse will come up.
Yeah.
And then you want to put after that a half, right? And what you'll get is 30 degrees. 30 degrees. Okay. So that was how did I find this angle? I used an inverse, right? Specifically, I used sine inverse. As you can see, there's cos inverse and there's tan inverse as well. Okay. Now it's just worth mentioning. It's not super important right now, but this thing over here, this thing here. Okay, I just want you to put a note on it, which you may refer to later if you come back to this, you know, next year or something like that. This part here, I'd like you to write. It only works when in a right-angled triangle. Okay. This is a bit weird. This is why I'm not going to dwell on this too much, but I want you to have it written down there so that later when you come back to this, if you're ever like, hey, what's this about, okay? Remember how I said +2 -2 always disappears, always cancels. ×3 divided by 3 always cancels. Sine inverse of sine actually doesn't always cancel so neatly, only when you're doing right-angled triangles. If you want to know why exactly, you can ask me about it afterwards, but I just want you to have that written down for now. Kyle first, yes.
For right-angle triangles, you do the same for cos, like it's like cos inverse.
Okay, should we do an example? I can do an example. Before you do that, did you have a question?
What's the like normal triangles?
Yeah, okay, in normal triangles, when it's not right-angled, right, And we will get to that eventually. You have to be a little more careful. And I'll show you why afterwards. But that's why I'm making a note of it now. Alright, just because Kyle asked for it, right? Let's do another one. Okay? Suppose we've got this. I'll do it like this. So I'm just thinking to myself, let's go here. One. Don't hurt yourself. I'm going to go back to calling this theta.
Theater.
Okay? So, here's the diagram, right? Again, the first thing you want to do is identify what sides have I got relative to the angle, relative to theta. Okay? And the answer is, well, this side's the hypotenuse, right? And the 1 centimeter that is measured there on the side, which one is it? Is it the opposite or adjacent? It's adjacent because it's right next to theta, right? This one over here is opposite, so the one next to it is adjacent. Okay? So this is why we started with that skill. It's an important sort of building block of the rest. So being that it's adjacent and hypotenuse, I'm after cos. I'm after cosine, okay? So I'll write down this equation. I'll say cos theta is going to be adjacent on hypotenuse. That's 1 divided by root 2.
So half
1 divided by root 2. Okay? So watch out for that square root sign. It does come up quite a bit. Okay. So now if I say, okay, I want to get rid of the cos just like I got rid of the sine here, right? I'm going to do cos inverse to both sides. And you can see, just like we did shift sine before, you can do shift cos, and that'll take you to cos inverse. Okay? So I'll write this. Cos inverse. Okay, like so.
I have an answer.
So then what happens? Over here, the theta's just left by itself, like so. For the same reason over here, it only works in right angle triangles. We'll explain why later. But then you pop this into your calculator, right? And you get 45 degrees.
Corrected. I wanted to say that.
So the same
Worked
ones.
hard for nothing.
Yep, exactly the same.
Corrected.
But if you get opposite and adjacent instead. Okay. By the way, just as a point of interest, the reason why I chose these particular lengths is because if I had 45 degrees, that's what you're telling me. And it's exact. It's not an approximation. What would this other angle be in the corner?
45.
It would also be 45. So what you got here is not just a right angle triangle, it's an isosceles triangle, right? And so in fact, these two angles are equal, so this side down here will also be 1 centimeter. And you can go ahead and check it out if you want with Pythagoras, it'll work you out.